So we'll start with page 37. In page number 37, the left-hand column, these questions are related to topic 3, that is the waves. The left-hand column of the table shows some possible speed of the sound wave, as you can see. The right-hand column, write down the medium, 1500. What could be the medium of 1500? Solid, liquid, or a gas? Sound travel fastest in solid and slowest in gas. So it is in between. So what should be? This should be liquid. What is the approximate speed of sound in a solid? Yeah, so it is about 5,000. So we'll write here a solid. And what is the approximate? Gas. So we just have to write solid, liquid, or a gas here, according to the question. Okay? The speed of a sound changes as the medium changes. Sound is a longitudinal wave, which means it consists of vibration are parallel to the direction of the wave and consists of compressions and the rarefactions. Figure 6.1 represent the series of the compressions and the rarefaction. So region of a high pressure we call compression and a region of a low pressure we'll call that as a rarefaction. So then compression, rarefaction, compression, rarefaction, compression, rarefaction, compression, rarefaction. On the figure 6.1, mark with the letter X and Y the midpoint of the two rarefactions. So we have to just mark with letter A, the midpoint of the two rarefactions. So this is one rarefaction, we mark that as X, and this is another rarefaction, we mark that as Y. State in terms of the pressure what is meant by a rarefaction. Rarefaction means region of low pressure because the particles have large space. In a compression, it is a region of high pressure. So for a sound waves, it is a region of low pressure. And how it's a region of low pressure? Because the particles have large spacing between them. Clear about this? This question is related to an echo or a reflection. You can see an astronaut sets up the mirror on the moon surface. So let's say this is a moon, and a laser beam is transmitted from the earth. So from the earth, he transmits a laser beam. And that hits the mirror on the moon surface and bounce back. On certain day, the time between the transmitting the beam from a point on the Earth's surface and receiving a signal back is 2.56 seconds. So that's a total time duration to travel and return back. The speed of a laser beam, because it's a light wave, the speed of electromagnetic waves, that is 3 exponent 8 meters per second. Calculate the distance between the Earth's surface and the moon. So whenever there's an echo or a reflection, what is the formula we use? We use the formula speed is 2d over t. Because whenever echo, it's twice the distance because it goes and then come back. Yeah. That's why it is twice. If it was only traveling from one end to another, then we will use the formula speed is distance over time. But this time is the total time and this distance is a twice. So if I need the speed is given, that is 3 into 10 to the power 8. 2 multiplied by d, the distance, which we don't know between the two. And the total time is equal to 2.56. So 2.56 is divided, other side multiplied. So it will be 3 exponent 8 times 2.56 divided by 2. So 3 exponent 8 times 2.56 divided by 2. What's the answer? Three exponent 8. Which is times 2.56. And that is divided by 2. So it will be 384 into 10 to the power 6 meter. That is a distance. Okay. Yes. Because there was a reflection, that's why we use a twice distance. If it was no reflection, then we'll simply use speed as distance divided by time. The next question is related to a lens, a converging lens or a convex lens. So figure 7.1 shows a converging lens and its principal axis. The points label F are each a principal focus of the lens. On a figure 7.1, draw two rays from top of the object to locate two rays from top of object to locate the image of object. So how we use two rays? First, a parallel light ray. We'll take from tip of the object, parallel light ray. From here, where it should pass through, if it's parallel to the principal axis. A parallel light ray, a light ray parallel to. From where it should pass through focus. One through the center of the lens, from where it should pass through, it should pass straight. Because the one through the center of the lens will, without any changing direction, it will pass straight. The position or the point where the two light rays will meet or intersect, it should be drawn exactly from tip of the object till the center of the lens and until the two light rays will meet. So the position or the point where the two light rays will meet, that will be the image. And this image, real images formed by a convex lens are always inverted. So it will always be upside down. If an object head is up, but the image head will be down. It's always, real images are always inverted. If it was a virtual image, then it will be upright and magnified. And virtual image can only be formed when the object is between the focus and the lens. We can also draw another ray because they ask us for two only, but we can draw a third. Like if they ask for three rays, then we'll draw this one. Through the passing through the focus will go parallel, and that will also meet at the same point. So it is irrespective, they all will meet at a single point. Underline three terms given to describe the nature of image produced by a converging lens as a magnifying glass. So if you use as a magnifying glass, image formed by a magnifying glass, is it diminished, means smaller in size? No. Is it enlarged? Yes, it is magnified. Or is it inverted? The magnifying glass no. Magnifying glass is forming an upright image, not inverted. Real images are inverted. Not when a convex lens is used as the magnifier. It's not real. It's not same size. Is it upright? Yes. Is it virtual? Yes. Figure 7.2 shows the path of a ray of a red light which is passing through a glass. When a refraction happens, violet bends the most because it's having the highest frequency, and red bends the least, which has the shortest, lowest frequency. So on a figure, we have to draw a path of a green. So this is the path for the red light. I want to draw for a green light. So for a green light, should I bend more or less? This is red. Green should bend. So it is Vibgyor. So it should have bent more or less? More. Because violet bends the most. We have the violet is N. So we have the electromagnetic spectrum, which include the visible light, including violet, indigo, blue, green, yellow, orange, and red. So red bends the least, violet bends the most, so green is in between. So it will also bend, but it will bend. Red is the least bending. So definitely the green should be below. Okay. So it's important to learn the order in terms of their frequency to identify the path which these radiation will follow when they move from one material to another. A laser produces a beam of a monochromatic light. State what is meant by the term monochromatic. The term monochromatic means light with single wavelength. Light with a single wavelength or a single frequency is called monochromatic. Don't say light with one color. That is not the right definition. Monochromatic is a light with a single wavelength. The next is a wave in a ray is incident on a glass. Glass block figure 7.1 shows a wavefront at air glass boundary. The arrow shows the direction of the travel. The wave undergoes reflection and refraction. On a figure 7.1, draw the wavefronts of the reflected. So how we can draw the wavefronts for the reflected? This is the direction in which the wave is entering. So when it strikes the surface, it will bounce back. Angle of incidence would be equals to angle of reflection. And only thing what happened during a reflection is the direction changes. When we draw the reflected wavefronts, these are the reflected wavefronts. What about the refracted wavefronts? As a wave travel from air to glass, it slow down. And these are the waves in air, like light waves. So it slow down and it will bend towards the normal. So this will be bending towards the normal. And what about the refracted wavefront? Because it's always perpendicular to direction of the wave. So this is the direction of the wave. These are the refracted wavefronts. So when the second arrow is representing a refraction. Refraction means property of a wave to change speed. And this one is representing reflection. In a reflection, only thing what happens is a change in the direction. But in refraction, not only, but in a refraction, it's the change in speed. And if the speed decrease, the wavelength will also decrease. And if the speed increase, the wavelength will also increase. Direction in a refraction may change depending on the scenario, but if it is passing along the normal, then there is no change in the direction. Okay, is it clear, this one? Is it clear, this one? A transverse wave is produced along a horizontal rope. The rope is much longer than the wavelength of a wave, like it will produce like it more than longer as a wavelength. In a space, sketch a diagram to show appearance of a rope and label 2 points, important features of the wave. So what we have, this is a rope which is producing a transverse wave. The top part of a transverse wave we call it crest. The bottom part known as a trough. The distance from the center to the maximum, what we call amplitude. The distance between the two successive crests, what we call that as a wave length. Okay? So this is the case for a transverse wave, which include light waves, water waves, microwaves. All electromagnetic radiation are like this. Next is a vibrating source on a ship produces a sound wave that travel through the ocean. The wave produced is a longitudinal wave. What is meant by a longitudinal wave? It's of 3 marks. So first thing, a wave in which longitudinal wave, the particle vibrate parallel to the direction of the wave. And propagate by series of compressions and rarefactions. So whenever there is a longitudinal wave, the best example, the sound wave. So what we will observe in a longitudinal wave, the particles vibrate parallel to the direction of the wave. Like these are the group of particles, they move to and fro by a series of a compression and rarefaction. What is the meaning of compression? Region of a high pressure will be a compression and a region of a low pressure will be rarefaction. So this is a 3-mark definition. Wave in which the particles vibrate parallel to the direction of wave, that will score 2 marks by series of compressions and rarefaction. As you can see, particles vibrate, has compression and rarefaction, and vibration is parallel. Now, the frequency of a sound is 800 hertz. That's the frequency. The speed of the sound is 313. What is the typical value of a speed of a sound in liquid? We just discussed that in the beginning. What is the typical value in liquids? Good, 1500 meters per second. Then use your value for B1. We have our value for B1. Calculate the wavelength of the sound waves in ocean. Ocean means liquid. So we'll use a formula V equals F lambda. Frequency never changes. So frequency is 800. And what about the speed? Dimension, we use our answer. So it will be 1500. We use the example 1500. The frequency is 800 and lambda. 800 is multiplied, other side divided. So 1500 divided by 800. So it's, in short, it is 15 divided by 8, which will give us 1.875 meter. But we write the answer in three significant figures, so I should write as 1.88 meter. Okay? Because after 5, there is an odd number, so we add 1, so that's why it is 1.88 meters. So when you write the answer, write in three significant figures. Another question, a similar question related to a sound. Figure 4.1 shows a loudspeaker that is producing a sound wave in air with a frequency 15,000 hertz, which is in or describe how cone of a loudspeaker produce this sound. So how cone of a loudspeaker produce this sound? So what will happen? If you have experience of touching a speaker, when I touch a speaker, I will feel the vibration. So what actually happened? The cone of the loudspeaker vibrate to and fro. The cone, this cone is moving in and out, to and fro, which collide with the air particles around it and push this air particle with the same frequency, having the same frequency. So this is what happened, like the cone of a loudspeaker vibrate, collide with the air molecules, which produce a series of compressions and rarefactions. Okay. So it's of the marks are always a reference. So 3 marks are there, and the points, as I mentioned, you can see alternating current is there. It causes the air to vibrate, producing compression and rarefaction. And the vibration of air will also be 15,000 hertz. Why? Because you already mentioned that a sound wave in air has a frequency of 15,000. So how to write this answer? The cone vibrate cause the air particles nearby to vibrate and produce series of compressions and rarefactions. So compression and rarefactions are produced, which has a frequency of 1500 hertz. Is it clear? The next part, speed of a sound wave in air is 330. Calculate the wavelength. So we already have the frequency in the previous part. We have the frequency that is given 15,000 hertz. And we need the wavelength. So we will write, it's 2 marks. Whenever a 2-mark question, 1 mark is always writing a formula. So V equals F lambda, where V is the speed of the wave, that is 330. F is a frequency, 15,000, and lambda is a wavelength. So it's multiplied, other side divided. So 330 divided by 15,000. What is the answer for this? 330 divided by 15,000. That will give us the wavelength, which is 0.022 meters. Okay. That's a very short wavelength because the frequency is high, so the wavelength will be shorter. If a frequency is low, then the wavelength will be longer. Now, this question is related to a diffraction. A loudspeaker is placed a considerable distance to the left of the barrier, and the width is double the wavelength. Means travel towards the barrier in the gap and then from away from barrier. So we have to show a diffraction of a wave. But as I already mentioned in the question, the wavelength, the width is double. For example, let's say this is 4 centimeter. So what will the wavelength, when you measure the wavelength, the distance between the two successive compressions? So in exam, when you draw, you should draw according to the scale. Like if the gap was 4 centimeter, then this gap should appear to be 2 centimeter if this was 4 centimeter. Okay, because I already mentioned that the width of a gap is double the wavelength. So wavelength is like 3 centimeter, width should be 6 centimeter. So width is given to you. So first you'll measure the width and the wavelength will be half of the width. So for this same question, let's say for the same question, if this width was 6 centimeter, what wavelength I should take? What should be the wavelength? The width is double of the wavelength. 3. So the wavelength should be half of it. So if the width is 6, the wavelength will be 3 centimeter. So after drawing like half of it, then we have to show a refraction. Because the gap size is larger than the wavelength. So as a result, what will happen? It will diffract, but it will diffract less. Smaller diffraction. So how we represent a smaller diffraction? Represent in this manner. If it was a maximum diffraction, then we'll draw the curve wavefront. So this diagram, in which you don't have to do much, you just have to show that the wavelength will be half of the gap size, and there will be a smaller diffraction, and the wavelength should not change. So make sure that the wavelength at which you drew the first should be there at the after diffraction as well, because the wave does not diffract as it passes through the gap. Next is figure 8.1 shows a ray of a red light incident on a side of a glass prism. For a red light, the refractive index is NR. The angle of incidence is 53 and angle of refraction is 30. Calculate NR. So the angle at which the red light incident, this is 53. And the angle at which it refracts, that is 30. The formula, whenever light travels from air to glass, and we need a refractive index in terms of the angle. So the formula for refractive index, it is sine angle I divided by sine angle R. That's a formula. If it travels from air to glass. But if it is from glass to air, if it was traveling from glass and then into air, then the refractive index will be equals to sine angle R over sine angle I. What if in exam you forget about the formula, you don't remember, then what is the simple? That always the numerator should be greater than denominator. Like the angle in the numerator should be greater than angle in denominator. So what are the two angles with me? I have 53 and I have 30. So which is
53 divided by
53? So I will just use It will be sine 53 divided by sine 30. What's the answer? Yeah, what's the answer? Yes, Hamid. What's the answer for this? Sine 53 over sine 30. Sine 53 divided by sine 30. That is sine 53, which is equivalent to 0.798, and sine 30 is there, which is equals to 0.5. So 0.79 divided by 0.5, which is equals to 1.46. So refractive index, they ask why we did not write a unit here, because refractive index is a ratio. Ratio is not having any units. On figure 8.1, sketch a line to indicate the path for the red light when it emerges from a label that has R. So when the light will emerge, it will bend away from the normal. So this will be the path taken by the red light. Because when it travels from air to glass, it will bend towards the normal. How this is toward the normal? The normal is always perpendicular to the surface. So if we draw this, this is bent toward the normal, and this is bend away from the normal. So the angle will decrease and then the angle will increase. The next is explain why the quantity refractive index does not have a unit. I just discussed that point. Why it does not have a unit? Because it is a ratio. Ratio is a comparison. Like if I say my mass is 80 kilogram and your mass is 60 kilogram or 40 kilogram. So when I compare, I will say I'm twice heavier than you. So it's a comparison. I will not say I will 2 kilogram heavier than you, 5 kilogram. It's whenever it's a comparison or a ratio, we don't write the unit. It's like how many times it is. So when we say a refractive index is 1.5, so it means compared to air, it has 1.5 greater tendency to bend light. If we say refractive index is 2, so it means compared to air, it has a tendency to bend the light twice as compared to that of air. So refractive index is not having any unit. It's just a ratio. For a violet, the refractive index of a glass is slightly larger. So if the refractive index is greater, the violet will bend more. For a ray of a violet light incident, on a figure, sketch a line to indicate a violet and label when it emerges, label that part as V. And when a ray of a white light is incident, so first thing we'll do that part in which we have to complete the path for the violet. This was red R. In which we completed the part. This is R. So then we have a violet. Violet bends more than red, so this will be violet. We label that as V. Because violet bends the most and red bends the least. Any color other than even red will bend more than red. Red is the least. It's a top line. Then in the next part, when a ray of a white light incident on the prism, dispersion is produced. A continuous spectrum of colored light. Like dispersion means like spreading of a wave when it passes through. And how the speed of a light in a glass depends on its frequency. And how this shown by dispersion of a white light in the prism. Statement. So what is the relation between the speed of a light and a frequency? the light with a higher frequency, if it is having a greater frequency, it will have a smaller speed. Why? Because when we drew the path for a violet, this was a path for the violet, and this was a path for the red. This was violet and this was red. So what we have other colors, but violet is having the highest frequency and red is having the least frequency. So higher the frequency, greater the change in speed, or smaller, which is traveling fast, because violet bends the most. So there's a greater change in speed of a violet as compared to that of red. That's why it bends more. So the means if the frequency increase, the speed will, higher frequency will travel at a lower speed. The wave with a high frequency will have a slower speed in a glass, and the wave with a lower frequency will have a higher speed, because, or change in the speed. So we can say the change in speed for a violet will be greater change in speed as compared to the red, which will have a smaller change in the speed. Okay, this is a very important point to relate them. So as you can see here, the larger frequency, smaller speed is there, or it will refract more. So statement here, the higher frequency shows greater change in speed. And what is the explanation for that? Because it bends the most. Like violet bend more than red. So if it light bend more, it means it has a greater change in the speed. So this was page number 47. Now we'll do some classified paper 2, which we'll discuss the MCQs.